First of all, I would like to thank the organizers for inviting me here and especially for organizing this very nice workshop. And my talk will be a bit different from what you've heard before, because up to now it was all highly sophisticated physics. And I mean, there's also some physics in my talk, but I will talk a bit more about technology, because we were entering the field, or are still entering the field at the moment, from a different side. And we are doing more technology, and you will see technology here, but you will also see some measurements. And yeah, as the title says, I'm talking about high-quality YIG nanoresonators. And first of all, I want to introduce the people who actually did the work. So it was all done at our university, but still people from different institutions. So Frank Heiroth started to develop the lithography. Frank Syrowatka also did a lot of electron microscopy. And then Philipp Trempler, he is now continuing the work on making the nanoresonators. Philipp Geyer did the simulations, which are shown in this talk. Christoph Hauser did YIG deposition. And people not shown here are Georg Woltersdorf and Ruven Dreyer from the optics group, and Stefan Ebbinghaus from the Institute of Chemistry, who by some magic is doing our targets for the PLD. So first, I will try to answer the question why we want to do YIG nanoresonators. But anyway, there are more people here in the audience who know better than I to do this. And you will basically see work from other people here in these few transparencies. Then I will show you how you can actually make them. I will talk about the structural properties and also finally about the magnonic properties. So one idea which comes to mind when you think about YIG resonators is quantum information processing, because one problem, as we have seen in quantum information processing, is that you want to transfer information from one excitation state to another excitation state. So for example, there has been work on coupling qubits to magnons already successfully demonstrated by people here. And, but it has also been demonstrated that you can couple qubits to mechanical oscillators. And why not use magnons and magnetoelastic coupling to transfer information to mechanical oscillations? And this was one idea. And another thing is, if you look at magnons and phonons, the coupling of magnons and phonons has also been demonstrated. You've probably heard about it this morning. I was not present, so unfortunately. But one drawback, and for me this is always a central drawback because I'm very application-oriented, is that these experiments were all dealing with basically, yeah, in my opinion, pretty large-sized YIG spheres. So this means we are talking about 50 microns, 250 microns, so almost millimeter size. And I'm always thinking about integration. So I want to make things small. Things should be scalable. You should be able to pack them close together. Because if you need one large YIG sphere to work on one qubit, and you need hundreds of thousands of them, then you have to make the YIG sphere smaller, or you need a different shape. But anyway, one thing which we also thought about in the beginning is it actually possible, because we are doing ferromagnetic resonance and we also want to do our own experiments on our resonators, is it possible to make resonators where we can actually match the mechanical frequencies to the FMR frequencies? And there are some examples from the past. For example, in 2003, the group of Michael Rukas already presented, in this case, I think, silicon carbide resonators, which went to the regime of 1 gigahertz. So here you can see the measurements from these resonators here. And you have a clear mechanical resonance at 1 gigahertz. And we also did some calculations. There's a very simple formula to calculate the frequency. And we can show that if we have a so-called doubly clamped beam, that means we have a YIG beam which is clamped on both sides. If it has a length of 1 micrometer and it has a thickness of 150 nanometer, then the frequency of resonance for the mechanical ground mode should be 1 gigahertz. And if you make it smaller, you can get even to frequencies of 2 gigahertz or 4 gigahertz, which is our typical FMR regime. So there we might be able to see direct interaction of the FMR frequency with a mechanical frequency. And typical shape for nanoresonators is either so-called cantilever, where you have one anchor point at one end, or a bridge with 2 anchor points at both ends. And now the question is how you can make these structures and how you can make them small. And for crystalline materials, the typical approach is as follows. You have to grow these materials normally at high temperatures to get good quality. And that means you cannot use resist-based lift-off processes because resists normally cannot stand high temperatures. So you normally go, in this case, towards sacrificial layers and wet chemical etching. And if you want to see how such a process works, you start with this kind of double layer. So in this case, the blue layer is the sacrificial layer. The red layer is the one where you want to make the freestanding structure. And you put a mask on top. And then you do some etching through all the layers. And finally, I don't know, no, now it works. And finally, you do some wet etching to remove the sacrificial layer, the blue layer, underneath the resonator. And then you have a freestanding resonator. But there a problem is, for YIG, which is grown on garnets, you basically have no sacrificial layers available. You might also resort to focused ion beam techniques, and there is one experiment published by the group of Aichi Saito, where a beam was fabricated, or in this case it was a cantilever, by focused ion beam. But you can see, so the size of this cantilever is about 80 micron. You might probably make it smaller, but still you have two issues. One issue is that you have this groove underneath, which has to be a certain size, even for a small cantilever, so it reduces the density of packaging which is available. And also ion beam techniques often damage the material. So the magnonic quality can suffer if you make it very small this way. So on the other hand, for amorphous or polycrystalline materials, there are other processes available. And the typical process is patterning by lift-off. And normally you use either multi-layer resist with different sensitivity, or you use electron beam lithography with different acceleration voltages. And here are just some typical examples. Here you can see a device which is about 1 micron wide and about 3 micron long, and you have 4 bridges which contact this device. This is done by a multi-layer technique, and if we use different acceleration voltages, we can even make more beautiful devices like these ones. You can especially make them pretty big. And so there is a technique to make bridges, but it's not compatible with crystalline materials. That's the problem. And you can already see that you have all kinds of shapes even available. If you do this, you're not limited to these doubly clamped beams or bridges, but you can make more complex structures. And yeah, now as I said, there are no sacrificial layers for YIG, so you cannot use this technique. And the deposition by liquid phase epitaxy or pulse laser deposition forbids patterning by lift-off because you will simply burn the resist in this case. Now the question is, is there a way to combine lift-off with crystalline YIG? And actually there is a way. And this way came to us a few years ago. It was in the frame of a European project. For us it was a kind of breakthrough because we managed to deposit YIG by PLD at room temperature, and in this case we basically deposit amorphous YIG. And then we anneal the material. So here you can see this is before the annealing. It's more or less amorphous as the Fourier transform is showing. And if you anneal it, you get very high quality material. And yeah, we were not able to find any defects, not even at the substrate interface. So this seems in principle perfect. And you have a perfect crystallization over at least 100 nanometer, and the substrate acts as a seed in this case. And what about the magnonic quality of this material? So we were very surprised, and we still don't understand why we have this. But the damping is the lowest reported up to now for PLD grown material. So we have here, for example, a 56 nanometer thick layer, and the line width is 1.3 Ørsted or 130 microtesla at 9.6 gigahertz, and the damping is 6 times 10 to the minus 5. So this is high quality material, and it's deposited at room temperature. And question is, so you can certainly combine the two, but the first question is, are PLD and 3D lift-off compatible? Because PLD and the normally done evaporation are still different processes. The next question is, up to now we have seen that we can crystallize the material over 100 nanometer. But if we have a bridge, we have 2 feet. And the question is, can we crystallize the material all through the bridge? And still, last question, I mean, for a thin film, which is directly on the substrate, we have seen that the quality is very high for magnons. What will be the case for the bridge if we can crystallize the material? And here I give you a brief glimpse into the process. It's just the schematic. So you use a standard PMMA resist, and then you use different acceleration voltages because the penetration depth of the electrons is very limited at low voltages. So you can do the low voltage exposure for the span of the bridge, and in some cases we also had some overhang at the end, so that we have even a kind of cantilever at the end. And then you use high acceleration voltage to expose the feet. And when you develop the resist, you see this kind of structure. The low voltage even gives you a nice undercut, which is necessary for the lift-off afterwards. Then you do the pulse laser deposition. This is how it should look in the end. And you see that very important, the top layer is completely separated from the bottom. And when you then do the lift-off, this is what you should have. And this is what we had. So you can see this is before the annealing, this is before the annealing, and down here it's after the annealing, so it's slightly bent. We have some strain, which we can understand because the substrate and the bridge itself, they have different thermal expansion coefficients, and now you heat the system up, it crystallizes, and then you cool it down, and you must get some bending. But anyway, the bridge is still freestanding, and the edges also you can see, they show some artifacts from the PLD. There we see the difference to evaporation. For evaporation, you can get very straight edges. With the PLD, you get more distribution of the material to the sides. But you can also see you can make very small ones. So this one has just a length of 500 nanometer. So in principle, you can say theoretically the mechanical resonance frequency of this resonator is 4 gigahertz. Then we had first a look at the crystalline quality. So what you see here now are all images taken by cross-sectional transmission electron microscopy. So we made a cut along the bridge. We took a slice out of the bridge, and we looked through the material. And you basically can see a very interesting effect. So I have not a lot of close-ups from this part, but I can tell you this is monocrystalline. But in the center, you have this. Somehow the pointer is not really working. In the center, you have this small defect. So that's here. And this is because it starts to crystallize on both ends. And you have some strain, you have some very slight tilt, and it meets in the center, and you get a kind of stacking fault. This is the only defect that we have in the span. And here also, we have some defects because here we have a lot of strain between the foot and the span of the bridge, but still the crystalline structure of the substrate can be transferred all through here. And this can not only happen over the scale of a few hundred nanometers, it can also done for higher bridges. So this one is even already a bit longer, but it's also higher. So this is almost 200 nanometer high. There we have a lot more strain, we have a lot more defects here, and we also have a very large extended defect here in the center. But what is maybe even more interesting is this one here, because this bridge is already almost 3 micron long. It's still monocrystalline, but you have the central defect here. But we can make very long structures this way, but we can also make them very small. And here, we even don't see any bending because of the strain, but it can also be. I have some reservations. I still have to check this. Maybe because we cut it out of the substrate, the strain was released. And if you would look at it on the substrate, there might be some strain in there. But anyway, we care more about the magnetic properties. But let's just look at the lattice. So we wanted to check whether the lattice is really clean or whether there is some tilt. And what we did is we took Fourier transforms on 3 different parts of the span, and we made it in 3 different colors, and we superimposed them. And already here you can see it. If you have a closer look, you can see they're slightly rotated. And as I said, you have some strain, and both sides of the bridge are slightly tilted against each other and against the substrate, but this tilt is only between 0.5 and 3 degrees, depending on the kind of bridge that you're fabricating. But this is all structural properties. So what about the spin properties? This is YIG, and you want to know about the damping, and you want to know about the spin waves. So the first thing that we did is, because this is what we had available in our group, we did ferromagnetic resonance on an array of bridges, because we expected to have a very small signal from the bridges. And so we made an array of 8,000 bridges, which should be nominally identical. We put them in the gap of a coplanar waveguide, or to say it the other way around, we put the coplanar waveguide on top. These bridges are rigid. They can stand optical lithography, they can stand lift-off, they can even stand ultrasonic agitation, which surprised me very much. Anyway, we did some ferromagnetic resonance measurement, and we find that at 8 gigahertz, we have a line width, so this is 2 delta H, 2.5 millitesla, so 1.2 millitesla. 12 Ørsted, some people may call this reasonable material. We have much better material for large areas, but still, this is on 8,000 bridges, and so if you then have 12 Ørsted, this means that either the lines are very small, or the bridges are very uniform. Otherwise, you would expect a much bigger line width. And then Georg Wolterstorff came. No, by the way, we already from this one, we extracted some damping. We could not measure at many frequencies because we also had overlapping lines, as you saw. But between 8 and 12 gigahertz, we could extract a damping which should be at least smaller than 4 times 10 to the minus 4. This is already a pretty good number. Anyway, then Georg Wolterstorff came and said, we can do better than this, because he has techniques where he can do time and spatially resolved MOKE, or time-resolved scanning Kerr microscopy. I will not go into the details, but he can really measure the magnetization dynamics by a focused laser. So it's a scanning technique, but he can look at the spin waves with a time resolution which he says can basically get into the range of 1 picosecond, and a spatial resolution of 300 nanometers. And so you can see, so these are now the measurements. So this is the homogeneous mode. We call it the homogeneous mode, where you have 0 nodes. And then if you go to lower fields at the same frequency, you get the Damon-Eschbach mode, because the field is oriented this way. And you can also get the backward volume mode, and we could see at least up to 6 nodes in this case. So this already looks very nice. And if you want to control this by theory, so also we did use mumax. And as I said, we had some very good, we have a very good student for simulations, and he did these simulations for the different spin wave modes. And the only thing that he had to adapt was the saturation magnetization of the material. Everything else came right out of the simulation. And the only thing where we have a slight difference is, for practical reasons, we did the simulations at constant field, because we do a step excitation and then we do Fourier transforms, and the measurements were done at constant frequencies. But anyway, it matches pretty much. So, and now we can measure the line width on a single bridge. Now, this is becoming more interesting. So we put a spot on a single bridge. We don't scan over the bridge, but we just measure the ferromagnetic resonance on this single spot. And the line width of the main resonance in this case is 140 microtesla at 8 gigahertz. So this means 1.4 Ørsted at 8 gigahertz. That's already a different number than 12 Ørsted. And this already corresponds to high quality thin film material. And so one question is, which I will tell you afterwards the answer, why is it so much more narrow than for the array? Do we have a spread of the frequencies for the bridges? Or it's the different part of the bridges, maybe? Anyway, here is the answer. So we did measurements on different bridges. And for different bridges, the measurements or the resonance frequencies may at least vary by 0.7 millitesla at 2 gigahertz. And 0.7 millitesla is about half of 1.4 millitesla. No, it's exactly half of 1.4 millitesla. It's almost half of 1.2 millitesla. And 1.2 millitesla was the line width that we saw. So this explains already the variation or the broader line width that we get for 8,000 bridges. And another question is, what about the different parts of the bridge? So we have the span of the bridge. So this is what we call a spatial image where we just look at the structure. So here is the span of the bridge, here is the post, and here is the overhang. And we can see that the resonance of the span, in this case, it is 81 millitesla. The resonance of the overhang is at 74 millitesla. And so you get an additional peak, and you can see indeed that here you have the resonance of the span and the resonance of the overhang as separate peaks, exactly separated by these 7 millitesla that we saw in the other measurement. So what about the damping? Yeah, this is the result that we achieved with the optical measurements. So for the optical measurements, we can get a damping. So we did measurements here from about 1 gigahertz to more than 8 gigahertz. And for a single spot, the Gilbert damping is lower than 2.4 times 10 to the minus 4. And this, I mean, it's still not as good as for our best thin film material, but on the other hand, for the thin film material, the best layers are about lower than 10 to the minus 4, but typical values which we can always achieve is 2 times 10 to the minus 4. And so that means that in principle, these layers or these resonators have the same magnetic quality or almost the same magnetic quality as our thin film material. And what's also interesting, the intrinsic line width at zero field, which we can extrapolate here, is 75 microtesla. And it's quite often that if you have very low damping, the intrinsic line width is still pretty high, or the other way around. You have a very low intrinsic line width, but a larger damping. But in this case, both the damping and the intrinsic line width are very low, so this is definitely high quality YIG, and we can get these nice resonances in the resonators. And finally, I want to show you that we have also optimized the process a little bit. So first, we also went for very simple bridges, and now we can do more complex structures. We knew this already, that it works for metals, but on the other hand, you can also do it with YIG. And probably I should better use my finger to point it because this thing is not working. So on the left-hand side, you see these squares. We can also do rings. On the right-hand side, you see a kind of round table. And if you want to know whether you can also get spin waves in these structures, so here, this is a measurement of spin waves in this round table mapped onto the SEM image. So you see that you can get different modes, and if you apply magnetic fields in different directions in square structures, you can get all different kinds of Damon-Eschbach modes or mixed modes between Damon-Eschbach modes and backward volume modes. But we still have a lot of things to explore. So at the moment, we're still at the beginning. And just to show you a few more things, just to give you a taste of what might be possible, the first thing that we did now is to explore how far we can extend the geometry. So here you see a resonator which is about 10 micron long. So 10 micron seems to be some mechanical limit. If we try to go beyond this, normally the structure collapses. And also, as you may already have seen, or you will see later during this conference, we were thinking, what can you do, for example, to accommodate whispering gallery modes? So here you have a round structure, and all the outer ring of the structure is completely suspended. We can make them in different sizes, and we can make the foot in the center smaller or bigger. Here you can see, in this case, the liftoff has not completely worked. So you have, this is 1 micron scale down here. So this is almost 1 micron, and it's going around a very large disk, but we can also make the disk quite small. We can make the overhang larger, we can make it smaller. So this process is very flexible in terms of possibilities for structures that you can make out of it. So as a conclusion, I hope I could convince you that we have a new process which not only allows us to make nanoresonators out of yttrium iron garnet, but you could also see that the material basically is monocrystalline. For me, it's still a kind of miracle because we've seen the crystallization over 5 micron during the annealing process. and I cannot understand why it works, especially because the unit cell of YIG is so complex. I think it's more than 100 atoms in a unit cell, but still it tends to order. The stoichiometry, I can tell you, is always a little bit off, but that's typical for PLD material. And the saturation magnetization for our thin films is usually a bit lower than for LPE-grown YIG, for example, or for bulk material. But anyway, the magnonic quality is very high. The crystal structure in this case is adopted from the substrate. And yeah, the line width which we get is as low as for the thin film material. The damping is a bit higher than for the thin film material because the intrinsic line width which we get is lower than for the thin film material, and that makes the slope of the curve simply a bit different. And also, it is an additive process, so you can grow the bridges where you want them. You can also make them very close together. If you have electronics which can stand 850 centigrade annealing temperature, then we can add the bridges afterwards. But on the other hand, the bridges are so rigid that we can add any kind of electronics after growing the bridges, so we can add waveguides. And meanwhile, I also got the first results, but they're still a bit noisy. That's why I didn't put them here. But we already got a signal from just electrically detected ferromagnetic resonance. So we had a single bridge, we put a coplanar waveguide, and we got a very clear line with a line width of 1.6 Ørsted. And so this means that we can do maybe nice experiments to look for the coupling to the mechanical oscillations, or maybe we can look at strong coupling between this material and superconducting resonators. And if you have a question afterwards, we did not yet investigate the properties at low temperature. But this is certainly the next step to do, as we can now measure one single bridge. And so then the next steps are certainly to look at coupling to mechanical vibrations. And then maybe other people, so that we don't have the expertise, maybe other people can look at coupling to qubits or integration of multiple devices for other purposes. In any case, as I said, we're coming more from the technology side. We're basically an FMR group. We're now probably with resonators and mechanics also starting to explore the field of spin cavitronics, but we don't have the expertise for more complex experiments. So collaborations are definitely welcome. If you have good ideas to do interesting experiments, just let me know. We're just trying to scale up the manpower a little bit. At the moment, we're limited to one student making the bridges. In the future, we will need more students making bridges for different experiments. And so maybe also I should say that we have 2 open PhD positions, one in ultra-fast spintronics and one for YIG-based spin Hall nano oscillators. And so with this, I would like to thank you for your attention.